Now I'm going to briefly review for you some of the basic aspects of the telecom communication system on board those satellites. This is just a block diagram of the main points in this transmission system. We have an input of many different signals. It could be either MPEG video, transport streams, digital audio, data, whatever. And all those signals have to be combined, and we call this process multiplexing. So once they are multiplexed, then we can already proceed. And the first thing that is done with all those data is to prepare them for transmission. And we normally call this process source encoding. So we are just coding the signals we want to transmit in such a way that could be adequate for the channel. But thus, we are just working on the information bits on the signals, which are all digital in this case, and we just prepare them for transmission. One of the first things that is done is just to encrypt them. That's to code them in such a way that they should be protected and no one could tamper with them. And we should maintain integrity and at the same time assure that no one could really, in an unauthorized way, extract the information and, let's say, eavesdropping on the talk. And that's something you always have to do with satellite transmissions, because there are many antennas that could be just listening to getting the signal and listening to the information you are transmitting. Now with this process, after encryption, then we now have a bit rate depending on the capacity of the channel and also on the data we are sending. This is RB, this is the number we are going to use, the letter we are going to use in the presentation. And now we prepare for the following part of the coding process, which is channel encoding, and that's to give the data strong protections to detect and correct the errors that will be in some way appearing during the transmission. So we are just giving tools to the receivers for detecting and correcting the errors. This process is normally called forward error correction, because we are just sending the data and the receiver will have to read that data and in some way compensate the errors. In some other cases, what is possible is to have a return channel by which, when the receiver has errors, asks the transmitter to resend the data. But in this case, we all the time have to do forward error correction. And now the output of the encoder is just the code rate. And with this part of the information, we now enter the modulation process. Here, what we do is just to prepare those signals, those bits, to be modulating the radio frequency carrier. And then we just go to the antenna. Up to the modulation level, we call those signals and those frequencies we are in use as baseband. We denote that this is just the basic information we want to send. Since the modulation process is nothing more than just shifting the information to a carrier frequency, so this part is associated with the carrier frequency, and this is just in a very high frequency band, but it contains the information. Here we have the transmitters, we have the connectors to the antenna, and the antenna will broadcast. So up until this level we have symbol, code, or bit rates, and now we start to talk about carrier frequency and modulation. And this is just the main block. This is just a short description of what I said before while commenting on the block diagram. Encryption is just the way to maintain confidentiality and authenticity of the information we are sending. And this is done by a set of keys that you know and hopefully nobody else knows. Channel encoding is just the process by which we add, for a certain block of codes, of words, we add check bits in such a way that we can then detect errors with that information. There are two important numbers in this process. The number of bits we add to the information bits, and the ratio of both the information read bits to the information plus redundant bits is called the code rate. And normally we will see this as a fraction of two numbers. This is the number of bits of information, and this is the number of bits encoded, the total number of code bits. And it's also the ratio of the input and output bit rates in the encoder. There are different families of codes, but here are listed some of the most, let's say, important or most frequently used. And Reed-Solomon and BCH codes are of the family of cyclic codes, and also low-density parity check codes. In the satellite case we are going to study, those are going to be the two types of codes we will be talking about. There are also a different scheme of encoding, which is just, instead of working on a set of fixed number of bits, we just keep a convolution. We convolve the train of pulses that they are going into the process. And those codes are called normally convolutional and depends on the rate and some other parameters. But fortunately, although they are complex to implement, we have a very powerful algorithm that was developed by Viterbi to decode in an optimum way. And things also could just be done in a more complex way by combining different codes. So when you concatenate either block codes or block and convolutional codes, and you add interleaving, that means you mix in time the bits, then you get a very powerful tool. And this is the basis for encoding. And then we have to talk about modulation, which is just assigning, transforming those information or those encoded bits into the carrier, and through the process of defining an alphabet of states or symbols and assign each one of those symbols to a group of bits. There are different schemes. We really have listed here the ones more frequently used in the satellite applications: phase shift keying or quadrature amplitude modulation, and also amplitude and phase shift keying. Those are the three most frequently used. And in the next picture, you have a representation, a graphical representation of those modulations. The first number, in this case 8, means we have 8 states. That means that you have 8 symbols, 8 modulation states. And each one then is associated with 3 bits. The representation here is in a complex plane, if you want, with 2 axes. This is the real, the in phase, and this is the quadrature 90-degree out of phase. And that means that we are just using 2 orthogonal signals of the carrier frequency to be modulated. If this is a cosine, then the orthogonal is a sine. Those 2 functions, you know perfectly well that they are orthogonal to one another, and that's the basis for the Fourier series. So we can play with the 2 and with them get different values of phase and different states of the modulation. And here you have the state, the 8 states, which are nothing more than 8 different phase states around here, 45 degrees each one of them. You have also the bits associated with each one of those states, and they are represented using what's called a gray code. And this is a simple and important one, because if you see from one state to the other, there's only a change in 1 bit. Only 1 bit changes. And this makes things easier in the processing of those codes. Now, this is for an 8. That means an alphabet of 8 letters, or a grouping of 3 bits. Now you go to 16, normally this number is always a power of 2. And here you have a quadrature amplitude modulation, and we have groups of 4 bits. And you see they are in a rectangular grid, and you have here once again the same codes. From this one to this one, only 1 bit changes. From this one to this one, only 1 bit changes, and so on. This is a very, very frequently used scheme, the QAM. And in the satellites we are going to talk about, you are going to also see this kind of modulations. Here we change amplitude and phase. Well, here the amplitude was just changing, but in principle nothing more. This plot is just more or less like this one, but instead of a rectangular grid, here we have a circular grid. And you have here the first 4 states, and then you have the 12 following on the outer side. And once again, from one to the other, there's only just change in 1 bit to the closest one. And those are the basic amplitude, the ideas for amplitude and phase modulations. You should also take into account the limits, in the sense the spectral efficiency you can get from this communication channel, and is governed by Shannon's law that tells you that the maximum data rate, or if you want the channel capacity for a given bandwidth, is related to the signal to noise ratio by a log of 2, and the units are here hertz, and in this case bits per second. There are 2 ways to increase the data rate for a given bandwidth. One is to increase the bandwidth, and this is what is done in the spread spectrum systems as the mobile phones. The other way is to have a fixed bandwidth, which is what happens in satellites, and then just see how the signal to noise ratio allows you to increase the bandwidth and the bit rate in this case. Now, let's just write briefly the relationship between the channel capacity and the signal to noise ratio. And this is going to be a Shannon limit. Now, we just change the log 2 scale to decimal logs, and this is what we have just to do here, just divided by log of 10 of 2. Now, if the signal to noise ratio is much larger than 1, then we can approximate this expression by b divided by 0.3, which is log of 2, and drop the 1 and have log 10 of the signal to noise ratio. If we multiply and divide by 10, then we simply have here the signal to noise ratio in decibels. So the channel capacity is roughly asymptotically tends to the bandwidth divided by 3 times the signal to noise ratio in decibels. Now, just to give you some data related to, let's take a satellite transponder bandwidth of 26 megahertz, and a signal to noise ratio of 10 dBs. Then you multiply 26 by 10 divided by 3, or you go to the expression and you get the exact number. And this gives you that with this channel bandwidth and this signal to noise ratio, you can transmit up to a maximum of 90 megabits per second. So this is just your limit. If you go above this limit, this number, then your errors would really become untolerated.